Our next speaker is Anna Flowers, and she's going to be talking about sequential space-filling designs. She's a fourth-year Ph.D. student in statistics at Virginia Tech. Go Hokies. She received a master's degree in statistics from Virginia Tech in 2023 and a bachelor's in mathematical statistics from Wake Forest University. Her research there focuses on Gaussian process regression, surrogate modeling, and active learning. And she, like Emma, was an intern here at IDA. Come on up.
Control both of them, or okay. Does the clicker control both the computer and
you can use
or
the key or the clicker.
Okay, thank you. Thank you everyone for coming. Like I said, my name is Anna Flowers, and I'm going to be presenting some of the work that I did as part of my summer internship at IDA last summer. I will just say, to address an elephant in the room, me and Emma did not try and wear the same outfit, but so if you get us confused, we won't be offended. This happens all the time anyways, so we made it worse. So I'm going to be talking about sequential space-filling designs that are going to be useful for the test and evaluation community. This is not going to be any new research that we've done. This is more of a literature review where we're trying to provide recommendations for the best existing methods for people who are in the test and evaluation community. Okay, so this project is motivated by the need to help find very good methods to help testers plan very good modeling and simulation studies. One very good design that one class of designs that's very good is a space-filling design. However, space-filling designs have the issue that they require you to choose the sample size that you're going to be looking at prior to any testing. So you have to choose all of your test points at once. And this could be an issue if you're performing a very expensive test because you have the possibility of wasting a lot of resources on unnecessary test points. One way to get around that is to use a sequential design, which is when you choose your test points either one at a time or a few at a time until you decide that you've collected enough data for some reason. And this allows you to design experiments without any knowledge of the final sample size, and you're less likely to waste resources by doing that because you can stop whenever you want. This can also be used in cases where perhaps you've already performed some test that has been designed, but it wasn't designed using design of experiments, and you want to add new test points in a very efficient way. This is a way that you could augment those tests. Okay. The goal of this project was to do a literature review of existing sequential space-filling design methods and then find and identify the ones that were likely to be of most use to the test and evaluation community. And later on in this presentation, I'll go into more about what we identified as being the most important criterion to look for sequential space-filling designs in T&E. After we found the sequential space-filling designs that we identified as being most important for the T&E community, we used a simulation study to compare the designs that we identified, and I will present that in this talk. And these results will also be in a paper that we're in the process of writing so that we can broadcast these findings to the broader T&E community. So to start out, I wanted to sort of ground where this research lives within the whole testing process. So as you might be able to expect, design of experiments, or I'll call it DOE in this talk in general, lies firmly in the test planning phase of a whole overall test. You use design of experiments to choose whatever test points you want to look at, and then you send it off to whoever's testing the method and said, look at these configurations of test points and give us the results. However, sequential design is a little bit different because instead of just choosing the test points and then sending those findings off to be tested, after you perform the test and then model whatever test points you found, you have the ability to look at the model and decide if you want to collect more information or not. And if you do decide that you want to collect more test points, you can go back to the test planning phase and you can keep doing this until you decide that you've collected enough test points for whatever reason. So what is DOE generally? DOE is a very large scope of research that is used to choose the best test points for certain scenarios, and it can provide different numerical measures of design quality through a lot of different metrics, some of which I'll mention in this talk. The oldest DOE methods, the classical DOE methods, tend to favor test designs with a lot of replicates and a lot of points near the boundaries. So to demonstrate that, I've shown some classical design of experiment methods on the screen, and I'll point out in particular this general factorial method. So if you imagine this cube you see in the screen as plotting three different variables, A, B, and C, where A is the height of the box, B is the width of the box, and C is the depth of the box, and you imagine these blue points as test points that we've chosen, you can see that the blue points, the test points that we've chosen, are all on the outside of that cube, or in other words, are on the boundary of the space, which means that if there is something interesting happening on the interior of the cube or the interior of the defined space, we're not going to be able to model it very well. So one way to get around this is to use a space filling design, as I mentioned before. These are especially popular for simulation experiments, and in general, they provide very good coverage of the operational space. Because of that, they are typically better at finding model trends than a lot of classical design strategies. So again, I have another example on the screen. On the left plot here, you can see the ground truth of some function. On this plot, the x-axis is one input and the y-axis is another input, and the color we see on the screen is the response of the function we're looking at. So we want to choose points that are going to approximate these colors as closely as possible, so we're approximating the value of the response. And I've shown the test points chosen by, on one side, the classical design, and on the left side, a classical design, and on the right side, a space-filling design that has 25 test points. Although the classical design does not look like there are 25 test points, that's because there are replicates that are on top of each other, so we end up with a lot of repeated observations that are not telling us anything. If we look at the predicted response here, which is the color of the left and right plots, we can see that the plot on the right much more closely matches that ground truth plot that we saw on the left, meaning that our space-filling design has made much better predictions here. So these are the types of designs that we are hoping to look at as part of this project. So when performing design of experiments, there are two ways that we can collect data points. The first is to use a fixed sample size, and this is often also called one-shot design of experiments. And this is where we set our sample size before we've collected any data and we choose all of our test points at once. So there are some benefits to using fixed sample size experiments. We are guaranteed to find the best design possible of whatever sample size we decide to look at based on whatever design criterion which we decide to look at. But of course, this has the possibility of us collecting way too many test points and wasting a lot of resources. And in other words, it may lead to oversampling. And if the test points are very expensive to collect, this is not going to be ideal. On the other side of design of experiments is a sequential design where instead of setting our total sample size before we do any testing, we choose new test points either one at a time or a few at a time, and that way we can just keep collecting data until we have enough, and we have a much smaller probability of wasting any time or resources, or in another way of thinking about it, we're much more likely to waste fewer resources. And that way we can stop collecting data when we have enough test points. And the definition of enough, I'm not going to go into that in this presentation because that's a broad question, but we're assuming we know in some way that we'll know when we've collected enough data. And for this presentation, of course, we're just going to be looking on the side of sequential design of experiments, which we find attractive because they are a lot more flexible when it comes to test design size than a fixed sample size experiment would be. So now I've shown why we might want to find space-filling designs and why we want to find sequential designs. And now what we want to do is combine those two ideas together and find designs that are both space-filling and sequential. And what this is really going to boil down to is we want to find designs that are going to be space-filling at every stage of the sequential design process. So on the screen, I've shown the two rows are two different sequential design methods that end with the same test design of 15 points. However, the way that they acquire these points is different in the upper and lower ones. And you'll see in the lower row of our sequential design that we are basically choosing points across the input space, and so in the bottom left one, there is a very large portion of space that's not covered. You might think it doesn't matter. They have the same ending design. But the whole idea of sequential designs is that we could have stopped at any one of these stages. So we want to make sure that if we were to stop at stage 1, we are still covering the operational space that we are looking at. And that's why we want to find sequential space-filling designs. So within the field of sequential designs, I started looking into space-filling designs specifically, but also the more broad sequential designs in case there was anything we missed. And I found that there are actually two types of sequential designs that were of interest to the test and evaluation community. The first was, as I've alluded to, a sequential space-filling design. This is a design that is much like what we saw in the previous slide, where we have designs that are space-filling at every stage of a sequential design process, and they are chosen based on space-filling criterion. There are many different space-filling criterion. One popular one is to maximize the distance between points, but there are lots of other ones. And these, just like a fixed sample size space-filling design, just aim to cover the operational space. And so it's a way of kind of covering all of your bases as you're collecting data points. But when you are doing sequential design, you actually have access to a lot more information than you would if you were doing a fixed sample size experiment. Namely, the fact that after you've collected some amount of test data, you have information about the response. And so if you model this response, you can see where the model doesn't know a lot of information. You can look at where the model variability is high or the model uncertainty is high. So the second method that we're looking at, adaptive sampling, which is also called active learning in a lot of places, is where we are going to choose new test points based on the model output, specifically in ways that are going to reduce model uncertainty. It turns out that if we have a very smooth surface that's not very wiggly, adaptive sampling is going to give very similar designs to space-filling designs because it's just going to try and fill out the space. But if we have more wiggly responses, we are going to benefit from using adaptive sampling because we can sample more points in the wiggly areas. So when I looked into these designs, I found many, many different methods that we can look for. I've listed some of them on the screen, and I've sorted them into those that are just space-filling designs and those that are adaptive sampling designs. And from this list that I compiled, I was looking for designs that were going to be applicable to the test and evaluation community and were going to be of the most interest. And we identified two criterion that were going to be the most important to the T&E community. The first one was that we were looking for designs that were able to accommodate both continuous and categorical variables simultaneously. So a lot of statistical designs are able to accommodate either all categorical variables or all continuous variables, but in T&E, we are very often dealing with tests where we have both of them, and there's just not that many methods that are able to do both. The second was that we were looking for methods that had very easily accessible software packages available, so we don't have to code all of these methods from scratch because that just makes the method much less usable. So after identifying those two criterion, we identified the four methods that are circled in green on the screen here, which are the maximum projection design, the slice Latin hypercube design, and then two different adaptive sampling methods. So you'll notice on the adaptive sampling side of things, I've separated the methods that have a continuous response and those that have a binary response. So if you'll recall, for adaptive sampling, we are going to be using the model output to identify where we should collect new points. And so that means our criterion for where the model is uncertain is going to depend on the response we're looking at. So we have different metrics for choosing new points for continuous responses and binary responses. And just as a note, in future slides, I'm just going to call this method adaptive sampling because we're not going to be doing both continuous responses and binary responses at the same time. But just to note, they are slightly different depending on what your response looks like. So now I want to go a little bit into what all of these designs are actually going to look like. So to do that, I've shown a sequential design acquisition for the three methods we identified, the slice Latin hypercube design, the maximum projection design, in adaptive sampling. For each of them, I've started with the same test design of 10 points and added exactly one new acquisition to show the differences between them. So the first one, I've just shown how to add points using a general Latin hypercube design. The sliced Latin hypercube design is an extension of the Latin hypercube design that can accommodate categorical factors that I'm happy to talk to you more about after the talk if you're interested, but I'm just going to explain the more general Latin hypercube design for this one. So ideally, what a Latin hypercube design would like to do is place every single test, it wants to divide up the input space into a bunch of equally sized rows and columns, and it would like to put each test point in its own row and column, which are what those dashed lines are on the screen. However, we already have a design that doesn't follow that protocol. So the best thing that the Latin hypercube design can do the next time it adds a new point is place that new test point in an unoccupied row and column. So you can see here, this red point on the right, which is the new test point, is in its own row and its own column, and it has just been randomly selected. So it could have chosen any unoccupied row and column, but that is the one that it did, and so that's where our new test point was added. The second design, the maximum projection design, seeks to optimize what is called the projected distance. And more specifically, it wants to add new test points in a way that the projected distance is as large as possible. What is the projected distance? So for every single test point, we have two input coordinates on the x-axis and y-axis. And what the projected distance does is look at the distances between those points one input at a time. So you'll notice that every single black test point lines up on the top to one blue line and on the side to one blue line. Those are the projections into one dimension and the other dimension. When we are trying to add a new test point, we want to add a test point that is as far from those projections in each dimension separately. So on the top, you'll see that there are two big gaps between those blue points. I don't think you can see my pointer, but from about 0.2 to 0.4 and then from about 0.6 to 0.9 or something. So we're going to pick a new point in one of those regions and add our new test point there. And separately, we're going to look at the projection of x2, which has a very large gap from about 0.0 to 0.3, and we're going to place our new test point there in the x2 dimension. And once we combine those projections together, we get that new red point, which you can see lines up with the red line on each dimension, and that's our new testing location. For the last method, adaptive sampling, this plot looks a little bit different. In addition to just showing the test points, I also have a color on the plot, which corresponds to the predictive variance at every single input location. And what we want to do for adaptive sampling is choose a new point that is going to decrease this predictive variance by as much as possible. And on this plot, the colors, the areas where the color is the most pink are where we have the highest predictive variance. So we're going to choose a new point somewhere in that pink area. And if you look at the slide on the right, again, that red dot has been chosen right in the middle of that pink area. So we are trying to we're trying to decrease the predictive variance by as much as possible. And I just want to highlight that all three of these methods are trying to add new points, either in a space-filling way or some other smart way, but they give us three different designs. The maximum projection and adaptive sampling put their new test point in almost the same place, but not exactly. And it is possible that for this Latin hypercube design, we could have chosen a new test point in that bottom right corner as well, because there are also unoccupied rows and columns there. But the point being, we can get different designs for these different test points, but they don't have to be completely different. The last thing to go over before I go into the simulation is to mention that when we do sequential design, we can add new test points either one at a time or in batches, which is what we call it when we add many points at a time. So on the screen, I've shown two different sequential designs that add 3 new test points, starting with a design size of 5, either one at a time or all 3 at a time. And you'll notice here again that we end up with 2 different final designs. Perhaps the batch selection on the bottom looks a little bit more space-filling, and that's because the more new points we add at a time, we can jointly optimize these space-filling criteria and make sure that when we place them, we'll be able to that we're able to place all of the new test points in a space-filling way, as opposed to if we do it one at a time, we're constrained to what we've already done. So once we've added a new test point somewhere, we are stuck with that design forever. So as I mentioned, using this batch method does tend to yield slightly better designs, and that's because as you increase the batch size, you're sort of going to be approximating a fixed sample size design, meaning that you can optimize all the space filling criterion for all the points at the same time. And this has its own drawbacks because as you increase the batch size, you're going to be more and more likely to waste resources, which was our original problem to start. So this is sort of a balancing act of making sure you have a large enough batch size to get good designs, but you're not wasting resources at the same time. So to test these methods, I did a simulation that is looking at the probability of kill of a weapon that we think has 2 continuous inputs and 1 categorical input with 3 levels. So on the screen here, there are 3 panels. Each one of the panels is one of the categorical levels that we're looking at, and each one has an x-axis and y-axis, which corresponds to the 2 continuous inputs. The color on the screen for all of these panels corresponds to the probability of kill for the weapon for that combination of inputs. And the areas where the plot is purple are where we have a very low probability of kill, and where the plot is yellow are where we have a very high probability of kill. Now, just to note, this plot that we were looking at, again, was the probability of a kill. So that doesn't mean that in that yellow region, every single time we're going to have a kill there. So just to demonstrate that, I wanted to show one realization of all of these input locations. So the plots that we see on the screen, each panel corresponds to the one directly above it. And on this plot, all of the white points are locations where we had a no kill, and all the black points are where we had a kill. And you can see that there are a lot more black points in the high probability of kill regions, but it's not at every single location there. So just keep in mind that there is some amount of variability here because we are looking at probability of a kill. So for this simulation, with this data set that I described in the last slide, we imagined starting with a test size of 12 points and adding new points either one at a time or in batch. We looked at both of them until we had a total of 48 points. And that is what is shown on this plot here on the x-axis, going from 12 test points all the way up to 48 test points. At each time we acquired new points, we collected the Breyer score using a holdout test to see how well our method was performing on the test points we had already collected. I looked at a total of 6 comparison methods that are combining both the 3 methods we looked at and different batch sizes. What do I mean by that? Not every method is available to be used with every single batch size. So you'll notice here, if you look at the legend, that adaptive sampling is only listed once, and that is because we can only use adaptive sampling to add points one at a time. And on the other side of that, the slice, slat, and hypercube design, we can only add points in batch. And in particular for the slice, slat, and hypercube design, our batches have to be a multiple of the number of categorical levels we had. So we had 3 categorical levels, so we have batch sizes of 6 and 12. And for the maximum projection design, we are able to use every single batch size that we use in the other 2. So we have batch sizes of 1, 6, and 12. In addition to our sequential method, we also showed the results from 2 fixed size designs of size 48, which is our ending test size, just to see how good we would have done if we had collected all 48 test points at once. The first one, which is the black triangle, is of a fixed size factorial design, really just as a sanity check to make sure that these classical design of experiment methods really are as bad as we think. You can see that that black triangle, that the fixed size factorial design is performing nearly as badly as our starting design of 12 test points for all of our sequential ones. So that is not a surprising result. I also included a design of a fixed size maximum projection design of size 48, which is the black square that is on the plot. And from that square, we can see that our fixed size design performs about the same as all of the sequential designs do at the same test size, again, 48. This may seem not very exciting, but it's actually a very good thing. Because if you remember, I said for a fixed size experiment, we can jointly optimize everything at the same time, so we are guaranteed to get the best possible design of size 48 with this fixed size design. So being able to get the same sort of results for a sequential experiment is a really good thing. But what is most important is the fact that when we're doing this sequential design, if we decided we were done after 30 test points, we could have stopped there and we wouldn't be wasting 18 test points of resources. I'm almost done. From this plot, you'll see all of the sequential methods honestly perform about the same. Maybe the slice Latin hypercube design with batch size 12 is a little better and the adaptive sampling is a little bit worse. But all in all, these methods are performing relatively similarly. So because of that, we're actually going to be recommending using the maximum projection design because of the fact that it is more flexible than these other designs. I mentioned before that adaptive sampling can only be used for one at a time acquisition, and slice Latin hypercube design has restrictions on the batch size, but maximum projection doesn't have any of these. So overall, it's going to give us the most flexibility. Overall, using sequential design is a good thing because it decreases the probability that we will waste resources. And when we are doing sequential design, we want to make sure that we still have good designs at every step of the sequential design process. When I did a literature review of these existing sequential space filling designs, we found 3 that matched the criterion we set, which were the maximum projection design, the slice Latin hypercube design, and adaptive sampling. And of those, we found the maximum projection to be the best because it is the most flexible. And in general, we would recommend using these in the greater TNE community. And I'm writing a paper on this, which hopefully will be done maybe over the summer, so that this information can be dispersed more widely. And the last thing to look at is, I mentioned that when we're doing sequential design, it is attractive because we can decide to stop at some early point in the process. But I never gave any information about how we know when to stop testing. And that is an open-ended question that we're still looking at answers for. So that's something to keep in mind. That's all I had. I'm a little over time, but I can answer any questions if there's time. Oh my god, I didn't change. Okay, there were more. Sorry about that.
Hi, that was fun. With respect to your the adaptive design, the one that you can't batch, and you can't batch it because you're putting the point exactly at the place of maximum variance.
Yeah,
in principle, you could optimize the average variance over the volume, in which case you could fling as many points as you want.
That is a much harder problem because it's much harder to predict what you're going to do to the variance when you add a bunch of points at a time. And if you're just looking at the point of highest variance, you're probably going to get a bunch of points in the same place, which is not going to be good.
Right, no, but if instead you take the average variance over the entire volume, what's going to happen is if your points start together, they're going to find an advantage in spreading apart. So you could actually try messing around with that.
Yeah, the issue with that is there is not very good software for doing that. Okay, thank you.